In this video, we will be learning about the prime factorization. Prime factorization is a way to break down a bigger number into smaller numbers by factoring them. The result of prime factorization is a few root numbers known as prime numbers. There are many reasons you may want to find the prime factorization, but first, we must go over the basics. Let's start by learning about prime numbers, which are the foundation to this entire video. A prime number is a number with only two factors, those factors being 1 and itself. For example, 2 is a prime number as its only factors are 1 and 2. Some more examples of prime numbers are 3, 5, 7, and 11. Because a prime number can only be factored into 1 and itself, there's no way for a prime number to be split up any further into smaller primes. This property is super important when talking about prime factorization. It's also important to note that 1 is not a prime number, and 1 will never appear in any prime factorization. What about the numbers that have more than two factors? These numbers are called composite numbers. Composite numbers have more than two factors, and they can be factored further into smaller prime or other composite numbers. For example, the composite number 6 can be factored as 2 times 3, and this would be the prime factorization of 6 because 2 and 3 are both primes that cannot be factored any further. Another example is the composite number 4, which can be factored as 2 times 2. Both 2's are obviously prime, so 2 times 2 would be the prime factorization of 4. Notice that both primes are the same. This is completely okay and doesn't mess up the prime factorization. There's a theorem that's very important relating to the prime factorization. That theorem is called the fundamental theorem of arithmetic, and this theorem states two things. The first thing is that a prime factorization will always exist. So for any number, no matter if it's in the hundreds, the thousands, the billions, no matter what number it will always have a prime factorization. And the second thing that the theorem states is that the prime factorization is unique to its number. So for any prime factorization that multiplies to a specific number, no other prime factorization will multiply to that same number. It's going to multiply to a different number. Let's try some harder prime factorization. We are going to try to factor the number 120. The best way to show prime factorization is to use a factor tree. So for example, we know that 120 is divisible by 10, so we can factor the number 120 into 10 and 12, like this. But we're not done yet. 10 and 12 are both composite, so we can factor them further. 10 can be split into 2 and 5, while 12 can be factored into 4 and 3. 2, 5, and 3 are all prime, but 4 is not prime. 4 is still composite, so we factor it further into 2 and 2. And now we circle all of our primes, and we multiply them together, and we get our prime factorization is 2 times 5 times 2 times 2 times 3. Notice that we could have done this in multiple ways. For example, I could have started by splitting 120 into 8 and 15 first. This is completely fine. Remember that by the fundamental theorem of arithmetic, you'll always end up with the same prime factorization in the end. So 8 can be split into 2, 2, and 2, while 15 can be split into 3 and 5. And we can see that the prime factorization is exactly the same. The order of the numbers in our prime factorization does not matter. As long as they contain the same prime components, which in this case is 3 2's, 1 3, and 1 5, then they are considered the same prime factorization. Now let's learn a more neat way to write the prime factorization using exponents. We can see that our product from before, 2 times 5 times 2 times 2 times 3, is pretty long and somewhat messy. To simplify this, we want to first group all the 2's together. And then we write 2 times 2 times 2 as 2 to the power 3, which represents that 3 2's are being multiplied together. And finally, we add in the 5 and 3 from before. So we get that the prime factorization is 2 to the power 3 times 5. Using exponents makes the prime factorization shorter and also more applicable, as we will see later in the video. A side note is that you want to write your primes in increasing order. So for example, in this prime factorization, we started with the prime 2, followed by the prime 3, and we ended with the prime 5. Let's try one more example. Let's factor the number 252. So first, we can factor 252 into 4 and 63. Then, we can factor 4 into 2 and 2, and 63 into 7 and 9. And finally, 9 is our only composite number left, so we factor 9 into 3 and 3. We take all of our primes, circle them, and we multiply them together, and we get that our prime factorization is 2 squared times 3 squared times 7. There are many reasons why you may want to find the prime factorization of a number, but the most common use of finding the prime factorization is to find the greatest common factor or least common multiple of two or more numbers. First, let's start with finding greatest common factor. We're going to be finding the greatest common factor of 120 and 252. We already know these prime factorizations, so let's write them out here. Now, to find the greatest common factor, we need to look at each prime separately. So the primes of 120 are 2, 3, and 5, and the primes of 252 are 2, 3, and 7. Let's look at the prime 2 first. As we can see, both 120 and 252 have a power of 2 in it. 120 contains the third power of 2, and 252 contains the second power of 2. We take the lower power, which is 2 squared in this case, and then we put it as part of our product in the GCF. Then we're going to multiply it by the next prime. So the next prime is 3, and the lower power would be from 120, which is 3 to the power of 1. And then we multiply that, and we get 2 squared times 3, which is 12. For 5 and 7, since 5 and 7 aren't shared between the two numbers, 120 and 252, we don't need to consider those. Another way to think about this is that 252 has 0 powers of 5, and 120 has 0 powers of 7, meaning that in our product, we multiply by the 0th power of 5 and the 0th power of 7, both of which are just 1. So it doesn't change our product. Finally, let's find the LCM of 120 and 252. Again, we're going to write out their prime factorizations, and we're going to do the exact same thing, except for LCM, we want to take the higher power instead of the lower power. So for example, we look at the prime 2, and we see that the higher power here is on the left. The number 120 contains 2 to the power of 3 in its prime factorization. So we put that as part of our product. And then we multiply by the next prime. So we look at 3, and the higher power here is 3 squared, which is part of the prime factorization of 252. So we multiply 2 cubed by 3 squared. And now this time, for 5 and 7, the higher power is actually going to be 5 to the power of 1 and 7 to the power of 1. So we're going to multiply them as part of our product. Another way to say this is that in 252, the power of 5 is 0. And in 120, the power of 5 is 1. The higher power in this case would be 5 to the power of 1. And the same logic works for 7. The higher power of 7 would be 7 to the power of 1. And so we multiply all of these together, and we get that the answer is 2,520 as our LCM. The main takeaway is that for GCF, you want to multiply all of the lower powers of each prime, while for the LCM, you want to multiply the higher powers for each prime.